Greetings. This video is a reproduction of my presentation at the 2017 Canadian Association of Physicists CAP Congress. The talk is entitled Domain Bridging in Melts of Starblock Copolymers. The research was conducted with Mark Matsen, and relevant links are in the description. Block copolymers are molecules composed of two or more types of monomers separated into different regions or blocks. I'll stick with two kinds, which I'll refer to as A and B type monomers. I'll color them red and blue respectively. This class of molecules is known for its tendency to microphase segregate into periodic structures like the ones shown here. When we say domain bridging, we're referring to the ability of a molecule to partly be in one domain and partly in another. For example, connecting this A-rich domain with this other A-rich domain. The simplest type of copolymer that can bridge domains is the linear triblock copolymer. It's also the molecule of choice for thermoplastic elastomers, the main application of domain bridging, so I'll spend a little time on it before getting to the stars. The triblocks typically used in thermoplastic elastomers are linear molecules as depicted here. The ends of the molecule are made of one type of monomer, which once again I'll call A-type, and the middle is made of B-type monomers. Their phase behavior, shown here, is well understood in terms of the volume fraction of A monomers, F, and the Flory-Huggins interaction parameter, Chi-n, which is large for low temperatures and small for high temperatures. At low Chi-n, or high temperature, the A and B blocks mix together forming the disordered phase, while at high Chi-n, or low temperature, the blocks microphase segregate forming periodic structures shown here. Thermoplastic elastomers form in the phases depicted on the left, where A blocks aggregate into small glassy domains that are held together by the B blocks, which form softer structures. The combination of the thermoreversible formation of glassy domains and the formation of molecular bridges that connect these glassy domains is at the heart of thermoplastic elastomer structure and function. Thermoplastic elastomers involve separable glassy domains, such as the spheres formed by the A block, immersed in a matrix of the softer material formed by the B block. Since the A-rich domains are glassy, it's difficult to pull the A blocks out of them. The glassy domains thereby act as strong links between molecules. In this sense, they resemble the covalent bonds formed during the vulcanization of rubber. Unlike those bonds, however, heating a thermoplastic elastomer melts the glassy domains, making the materials thermoplastic. For the purposes of this talk, it's perhaps more useful to think of the material as a set of glassy domains connected by molecular bridges. The reason that triblocks are often chosen should be clear. It's important that there be A blocks at both ends of the molecule because this allows for the formation of molecular bridges between different glassy domains. These bridges resist applied forces and strengthen the material. Next, let's see what happens when we apply a stretching force to the material. When a force is applied, the softer domain can deform, but the crosslinks between the glassy domains hold the material together and preserve its structure, making it elastic. Loops, however, do not contribute to the elasticity. We're therefore interested in calculating the fraction of molecules that form molecular bridges. This bridging fraction has been calculated for linear triblocks and is shown here. In the sphere phase, about 80% of molecules form molecular bridges. In the cylinder phase, this reduces to about 60%, while in the lamellar phase, less than half of the molecules form bridges. Our next step is to turn to Starblock copolymers. Let's see if they can do any better. Most of this talk concerns 9-arm stars, which are structured as depicted here. As with the triblocks, we need the A blocks, drawn in red, to form small glassy domains, connected by the B blocks, which form a soft matrix around these glassy domains. The phase behavior for Starblock copolymers looks very similar to the linear triblock. The disordered phase is found at small Chi-n, and the usual periodic phases are found at higher Chi-n. In order to calculate the bridging fraction, we need to take a closer look at the statistics of parts of the molecule. Consider one arm of a Starblock copolymer. The position on this arm is parameterized by the variable s, where s equals 0 at the free end and s equals 1 at the other end of the arm, the junction point for the star. For s from 0 to f, the monomers are of type A, s equals f is the AB junction, and for s from f to 1, monomers are of type B. Now imagine that you pin a particular monomer at molecular position s to spatial position r. You can calculate the partition function for the portion of the molecule from 0 to s. This partition function represents a sum over all possible configurations of that part of the molecule subject to this pinning constraint. We call this partial partition function a propagator and denote it Q. The propagator obeys this modified diffusion equation, which we solve numerically. The diffusion equation is solved with a uniform initial condition at s equals 0, since the free end is, well, free. There's also a back propagator, Q dagger, for the rest of the arm, and it's calculated similarly, but with one side of the diffusion equation multiplied by -1. This is because we are, in effect, integrating in the opposite direction. The initial condition for the arm's back propagator is also different, since the arm at s equals 1 is not free. The details are given in the paper if you're interested, but essentially the initial condition is a combination of the propagators for the other arms in the star. Once they've been calculated, the propagators can be combined to find the partition function for the entire molecule, as well as the concentration of molecular segments and other statistical properties of the molecule. To calculate bridging statistics, we start by considering the equilibrium structure shown here. In this example, we've chosen the cylinder phase for ease of visualization. We then consider one unit cell for this periodic structure. It consists of one A-rich domain as well as its immediate vicinity. This region will be referred to as the first cell, and it's shown here outlined in green. We want to calculate probabilities related to different numbers of arms connected to this first cell. Keep in mind that each unit cell for the system is essentially the same, so arguments that I'm about to present apply equally to all of the unit cells. To calculate the propagator for an arm attached to the first cell, we restrict the AB joint at s equals f to lie within this cell by setting the propagator to 0 outside the cell. This is equivalent to calculating the propagator in such a way that it only considers configurations where that arm is attached to that cell. We can then propagate to the center of the molecule as usual, giving us the propagator for the s equals 1 end of an arm that's attached to the first cell. To get a feel for what this quantity means, you can think of it as a non-normalized probability distribution for the B end of an arm that's not attached to a star. Since we're interested in the behavior of stars, not isolated arms, we need to consider the rest of the molecule as well, including arms that are not attached to the first cell. By subtracting the restricted propagator from the unrestricted propagator, we can obtain the propagator for arms that are not attached to the first cell. We want to calculate arm statistics for a star with a total of capital M arms. We consider the case where little m arms are attached to the first cell and the rest are not. The first step is to calculate Qm of R, which is the partition function for a star with its center at position R and a total of little m arms attached to the first cell. This partition function is calculated as a binomial distribution. The first factor is the number of ways of choosing little m arms from a total of capital M arms. The second is a partition function for little m arms constrained to the first cell. The last factor is the partition function for the remainder of arms which are not attached to the first cell. We can then go on to calculate the joint distribution Pm of R, which gives the probability density that an arm attached to the first cell will be part of a molecule with a total of little m arms attached to the first cell, while having a molecular center at position R. To be clear, imagine that you could reach into the melt and grab an arm attached to the first cell. This joint distribution gives the probability that the arm that you grab is attached to a molecule with exactly little m arms attached to the first cell. This probability is expressed as a distribution function of the position of the molecular center. Later, we will integrate out the position dependence of the joint distribution to obtain the marginal distribution. This gives the probability that an arm attached to the first cell is attached to a molecule with exactly little m arms attached to the first cell. Let's start by calculating bridging statistics for the simple case of the lamellar phase formed by a 9-arm star. The region on the left is the first cell. These curves represent the joint distribution, Pm, as a function of molecular center position, Z, given that either 9, 6, or 1 arms are attached to the first cell. When all 9 arms are attached to the first cell, molecular centers tend to be close to its A-rich domain, just as you would expect. When 6 arms are attached to the first cell and the other 3 are attached to the adjacent cell, the distribution is more centered between the two. When only one of the 9 arms is attached to the first cell, the distribution is shifted to the right. Our next step is to remove the position dependence by integrating it out. This gives the probability that an arm attached to the first cell will be attached to a molecule with a total of little m arms attached to the first cell. The result of this integral, the marginal distribution, is shown here for the lamellar phase, and is given as a function of little m. The low value at m equals 1 shows that you're unlikely to pick an arm that's attached to a molecule with only one arm attached to the first cell. It's also unlikely to pick an arm attached to a molecule with all 9 arms attached to the first cell. The peak at m equals 6 shows that if you were to pick an arm at random, it's most likely to be attached to a molecule with 6 arms attached to the first cell. The lamellar phase is a nice test case, but it's time to increase the dimensionality of the problem and consider the cylinder phase. Once again, we start with a sketch of the phase of interest. The A domains are outlined in red. The first cell is now shown in green, and the joint distribution is shown in purple. If there's only one arm attached to the first cell, as illustrated, molecular centers are generally far away from its A-rich domain. This is because arms are generally attached to other adjacent A-rich domains. When 2 arms are attached to the first cell, the molecular centers are generally closer to its A-rich domain. When 4 arms are attached, molecular centers get even closer. And finally, the molecules with 9 arms attached to the first cell have molecular centers that are very close to its A-rich domain. Once again, our next step is to get rid of the position dependence of the joint distribution by integrating over R. This will give us the marginal distribution. This marginal distribution gives us the probability of choosing an arm attached to a molecule with little m arms attached to the first cell. As with the lamellar phase, there's a low probability of choosing an arm on a molecule with only one or with all 9 arms attached to the first cell. The peak is at 4. Notice that this is decreased as compared with 6 in the lamellar phase. The curvature of the cylinders allows stars to spread out more, causing this shift in the peak. Also notice that stars can bridge 3 or more domains simultaneously, a behavior that's impossible for linear triblocks, since they only have 2 ends that can attach to A-rich domains. Once again, the next step is to increase dimensionality, this time to consider the sphere phase. As before, the A-rich domains are shown in red, except for the first cell, which is shown in green. The distribution of molecular centers is purple. If only one arm is attached to the first cell, molecular centers are generally spread out. As we increase the number of attached arms, molecular centers get closer to the A-rich domain of the first cell. Our next step is to, once again, integrate out the R-dependence of the joint distribution to obtain the marginal distribution. We see that the peak in the marginal distribution has moved down from 6 in the lamellar phase to 4 in the cylinder phase to now just 2 in the sphere phase. The marginal distribution is also tiny for m equals 9, meaning that it's very unlikely to pick an arm attached to a molecule with all arms attached to the first cell. Any arms that aren't attached to the first cell will be attached to other cells. The fact that the marginal distribution is so tiny at m equals 9 means that the vast majority of molecules are forming molecular bridges. We can also see from the joint distribution that molecular centers are concentrated in regions close to multiple A-rich domains. This suggests that bridging molecules tend to form bridges between several different domains, not just 2. Our next step is to use the marginal distributions to find bridging fractions. The bridging fraction is the fraction of molecules with arms in more than one domain. That is, the fraction that form bridges between domains. As discussed earlier, this is important to thermoplastic elastomers as it's these bridges that give the strength and elasticity to the resulting materials. We start with a 2-arm star, which is just a linear triblock, and we see the same results we saw earlier. Adding one more arm to make a 3-arm star increases the bridging fraction in spheres from about 80% to about 95%. There's also a substantial increase in the bridging fraction for the other 2 phases. Increasing the number of arms to 5 further increases the bridging fraction. By the time we get to a 9-arm star, virtually all of the molecules are bridging domains. Our results for the sphere and cylinder phases suggest that these molecules are bridging not just 2 but several different domains, further adding to the strength and elasticity of the material. In this talk, I've presented a method for calculating bridging statistics for complicated polymer architectures and applied it to Starblock Copolymers. The bridging fraction of stars increases rapidly with a number of arms, and stars tend to bridge multiple different domains. This method is versatile and can be applied to a wide variety of polymer architectures as well as statistical quantities. This brings me to the end of the talk. Once again, if you'd like more information, please see the paper linked in the description. I hope you enjoyed this rendition of domain bridging in melts of Starblock Copolymers. Thanks for listening.